Hello everyone, and in this video I just want to do a quick introduction to proof by contradiction. So I'm just going to do maybe 3 or 4 examples of proof by contradiction. Really important idea. And we're going to start off with the classic one, to prove by contradiction that √2 is an irrational number. Now, for proof by contradiction, we always start off by assuming the opposite, which is sometimes called the contrapositive statement. So what we're going to assume is, if we want to show that √2 is irrational, then we're going to start off by assuming the opposite. Okay, so we're going to assume that √2 is rational. Now, what do we mean by rational? We mean that it can be written in the form and can be written in the form a over b, where a and b are integers with no common factor. That's super important. Apologies for my horrendous handwriting there. So yeah, we're going to assume that √2 is a rational number and that it can be written in the form a over b, where a and b are integers with no common factor. So we start off by writing √2 is therefore equal to a over b. Now this is super important, this assumption, especially the fact that they're integers and that it has no common factor. Don't forget that bit, that's really important. So we start off writing down √2 equals a over b, so we square both sides. So we have that a squared over b squared is equal to 2. We then times both sides by b squared, so we have 2b squared is equal to a squared. Now, 2 times something, if we've got 2 times an even number, the answer is even. And if we have 2 times an odd number, the answer is even. So if you've got 2 times something, then by definition it has to be even. So that means that a squared is even. Now, if a squared is even, that in turn means that a has to be even as well. Now, why does that mean that a has to be even? Let's have a think about that. Because if you've got a squared and it's even, it has to have come from even times even, which equals even. Because it can't have come from odd times odd, because odd times odd is odd. So by definition, if a squared is even, then it must have come from even times even, which means that a is even. Okay, so far we've basically said that a is even. Now, if a is even, it could be written as, we're going to say let a equal 2 times some other number n. So therefore we're going to sub that back into this stage now. So we've now got that 2b squared is equal to a squared. So 2b squared is equal to 2n squared. So therefore 2b squared is equal to 4n squared, just expanding the bracket. And then we can cancel a factor of 2, which gives us b squared is equal to 2n squared. Now this, using the same logic as from before, this means that b squared is even, because it's 2 times something, using this logic from up here, which in turn, using the logic from over here, means that b is even. So therefore b is even. So if we've now concluded that a is even and b is even, and this is our contradiction. So that is our contradiction, okay, because we assumed initially that a and b were both integers with no common factor. And what we found in actuality is we found that if we assume that, we find out that a and b actually have a common factor of 2. And that contradicts our original assumption. Okay, so contradiction as common factor of 2. Therefore, √2 is irrational. There we go. So therefore √2 is irrational. So that's the proof for the irrationality of √2, which is a super, super important proof. And yeah, one that, you know, you could easily be asked on your exam. Okay, the next one I want to look at is, again, a very, very popular kind of one for EDEXCEL. I've seen this particular one come up on a number of occasions in various forms. And I think it's important to know how to deal with this one because EDEXCEL seem to like this one. So let's have a look at this one. Here's another example of a proof by contradiction. Okay. So what have we got with this one? It says prove by, because I know that in my experience, people find this one a little bit confusing. So it says, prove by contradiction that there are no positive integers p and q such that 4p² minus q² equals 25. Okay, so again, we're going to assume the contrapositive statement, the opposite. So we're going to assume that there are positive integers such that 4p² minus q² equals 25. Okay, so that's our assumption. We're going to assume the opposite. Assume that there are positive integers p and q, such that 4p² minus q² equals 25. Okay, so we've assumed the opposite there. Okay, so let's have a look at that. Now, the first thing we can say is, and again, students sometimes don't recognize this, 4p² minus q² is the difference of two squares. So we can think of that as 2p minus q times by 2p add q. Okay, so I've written that as the difference of two squares there. Now we've got two options that are available for 25. Either 2p minus q and 2p add q could equal 25 times 1. That's one option. Or perhaps 2p minus q times by 2p add q could equal 5 times 5. So we've got two different options, okay? Now let's examine these one at a time. Let's examine this first combination. Now that would mean that 2p minus q would equal 25 and 2p add q could equal 1. Okay, for example. Now at this point some students say, but hang on a minute, couldn't it be the case that 2p minus q is 1 and 2p add q is 25? In other words, couldn't these two just be swapped over? And yes, that could be the case. And if that's the case, we've still got the same set of equations. All that would do is it would swap over which one is p and which one is q. Okay, so it's if you swap them over and you write 2p minus q is 1 and 2p add q is 25, it's still the same set of equations. It just kind of like swaps over which one is called p and which one is called q. Okay, and then here for the second one, our second variant is, this means that 2p minus q is 5 and 2p add q is also 5. And because they're 5 and 5, there's only one possible pairing anyway for that one. Now, what happens is if we put these into our calculators and we solve these two systems of equations, what we find out is this one gives us p is equal to 2.5 and q is equal to 0. And this one gives us p is equal to 6.5 and it gives us that q is equal to 12. Now, this contradicts our original assumption because our original assumption was that there are positive integers such that p and q, such that 4p² minus q² is 25. But we found that the solutions to the only possible combinations give us, in fact, decimals in both cases. Okay, so that contradicts our original assumption. Okay, so we're going to put then this is a contradiction. This is a contradiction. This is a contradiction as there are no integer solutions. No integer solutions. No integer solutions. So therefore, we can conclude that there are no positive integers such that 4p² minus q² equals 25. And that's it done. Oops, there we go. So let's have a look at it again. We just basically start off by assuming the opposite. We assume that there are positive integers such that that is the case. This gives us two different options in terms of systems of equations that we can solve. And we find that in the solution to both of those, we end up with decimals as part of our answer. So therefore, that contradicts our assumption that there are positive integers. And therefore, we find out that there are no, the opposite must be true. So there are no positive integers, okay? And then the last one that I would like to look at on this one is one that I think is quite intriguing. Let's just have a look at this last one. This is from, I think, mock set 3, but I quite like this one. It's an interesting one. Again, you know, you may not have seen this one. It's not kind of like widely discussed. And it's this second part here that I'm interested in. Use proof by contradiction to show that log⁴ of 5 is irrational. Okay, so we're gonna, this rather works like the √2 one. We're going to assume the opposite. We're going to assume that log⁴ of 5 is rational. Okay, in other words, we're going to assume that log⁴ of 5 can be written in the form of a over b, again, where a and b are integers with no common factor. So we put a and b are integers with no common factor. Okay, all right, so let's do that then. So let's write it. So we're going to say log⁴ of 5 is equal to a over b. So now we're going to reverse the logs, which means that we're going to write that 5 is equal to 2 to the power of a over b. That's reversing the logs. And then what I'm going to do is I'm going to put both sides to the power of b. So I've got 2 to the a over b, put both sides to the power of b. Now, because here for integers, I've got a over b times b now, okay, and a over b times b is just a. So this now becomes 5 to the b is equal to 2 to the a. And this is a contradiction. This is a contradiction because 5 to the b is never going to equal 2 to the a. And we can say, therefore we can say that log⁴ of 5 is irrational. Now, I really like that one. I think that's quite interesting. Just for interest, why is it the case here that 5 to the b is never equal to 2 to the a? Well, you might remember, if we go back, this is just to explain why, in case you're wondering why that's the case. You might remember back in like year 7, you know, when we were doing like kind of prime factor decomposition of numbers, yeah. So we would say, okay, 36 is 6 times 6. And then we would say that is 2 times 3, and that is 2 times 3. And we put circles around them to show that they're prime. And then we used to say 36 is equal to 2 squared times by 3 squared, okay? Or the other option is you've got that, or you've got a number that is prime itself, okay? Now, basically, what we didn't realize it back in year 7, but what we were learning there is one of the absolutely fundamental facts about numbers. And that is that all numbers are either prime or they're made by multiplying primes together, okay? In other words, every number that exists has a unique prime factorization, okay? Like, for example, let's say I make some random number up in the old, this is the old outgoing calculator from Casio. Let's have a look. I'm just making some number up there, soon to be replaced. So there's a number, 1, 2, 3, 4, 5, 6, 7, 8, 9. And on this old model of the Casio calculator, they had this button here called fact, okay? When I press that button, it breaks it down into its prime factorization. So actually the number 1, 2, 3, 4, 5, 6, 7, 8, 9 is actually 3 squared times that number there, which is also prime, okay? So basically, because each number has a unique prime factorization, that means that 5 to the power of something will never, ever, ever equal 2 to the power something. Okay, no matter what the values of b and a are, those numbers are never going to be the same. Okay, and in fact, again, you may not have heard of this, but there's a very famous kind of like thought experiment about infinity from David Hilbert, and it's called Hilbert's Hotel. Hilbert's Hotel. You don't need to know that, that's just background. So if you want to look up Hilbert's Hotel, but Hilbert's Hotel deals with this kind of like idea about the fact that each number has a unique prime factorization. Okay, so suffice it to say, in this A-level question, which you could be asked on your exam, we assume that it is rational. We find out that we get to this statement here, which is a contradiction because that can never equal that, and therefore we conclude the opposite. So therefore we say that log to the base 2 of 5 is in fact irrational. Thought that was quite nice because of the way it uses this subtle idea from maths. Okay, there's a few little proof by contradictions for you. I hope that you found that helpful, and I'll see you in the next video.